Next application of double integrals we have is surface area. It turns out there's two different formulas for surface area depending on how the surface is presented, but this section will talk about for explicit surfaces. That is, surfaces that are of the form z equals f of xy. So if your surface was given implicitly and you either couldn't solve for z explicitly, or there were some other reasons that you wouldn't solve for z, then you can't use this technique here. So just like with arc length, if you recall, the formula for arc length was the integral from the starting point to the ending point of the square root 1 plus f prime of x squared dx. Now the formula for surface area is related to this. It looks actually similar. Surface area is the double integral now over some region, the square root of 1 plus the partial of f with respect to x squared, the partial of f with respect to y squared. And this is now with respect to area. So if you look at the integrand, it looks similar. It's the square root of 1 plus then the sum of the squares of all the partial derivatives. And this gives us the surface area of the region. Let's look at an example. Let's say we had the function z equals 9 minus x squared minus y squared. We wanted to find the surface area of the part of the surface that's above z equals 0, above the xy plane. So first off, let's see where it crosses the z equals 0. If we plug 0 in for z, we've got 0 equals 9 minus x squared minus y squared. If we move the x's and y's on the same side, we've got x squared plus y squared equals 9. Now, as the z value increases, we see that these circles are going to get smaller and smaller. In fact, if you look at z equals 9, we get 9 equals 9 minus x squared minus y squared. We move the x and the y over, you move the 9's together, and we get just a single point. So this is kind of a degenerate circle of radius 0. So that means the region we're integrating over is everything inside this circle. So R is this disk of radius 3, centered at the origin. So that's our region of integration. Now, because our region is a disk, we should probably integrate in polar coordinates. So our surface area is then going to be, I'm just going to write this out, this is the double integral over the region, square root 1 plus, now we're going to take the partial with respect to x, which is 2x squared, which is negative 2x, and we square it. And then we take the partial with respect to y, which is negative 2x, negative 2y, and we square it. And this we're integrating with respect to area. Now let's switch over to polar because our region is circular. So in polar coordinates, this is now going to become 1 plus, well, this is 4x squared plus 4y squared, and that's 4r squared. And now, remember, when we switch over to polar, we've got this r to deal with, this integrating factor of r, dr d theta. We've got a full disk, so the r is going from the inner radius to the outer radius. And the thetas, since we've got a full disk, are going from 0 to 2 pi. Okay, and now the inside factors up. This is actually just a function of r, so we can use the box theorem to rewrite this as the integral from 0 to 2 pi of d theta times the integral from 0 to 3 square root 1 plus 4r squared times r dr. Okay, this first integral from 0 to 2 pi of d theta is just theta from 0 to 2 pi, which gives us 2 pi for the first integral. Now the second one, we'll have to do this by u sub. Let's let u be the inside, 1 plus 4r squared. So du is then 8r dr. So we need an extra 8 in here. Put the 8 in here and a 1/8 on the outside of the integral. So this is going to give us 1/8 the integral of square root of u du. And then we've got limits of integration, which I'm just going to write it as stars for now. Now if we integrate this, this is going to give us pi over 4 on the outside of the integral. We do the power rule here. We've got u to the 3/2 times 2/3 evaluated at our endpoints. And then let's plug this thing back in for u. So this is going to give us, if we reduce these, pi over 6 times 1 plus 4r squared to the 3/2. Now, since we're back in terms of r, we can plug in our r limits, 0 and 3. So this gives us pi over 6 times, now if we plug 3 in here, well, 3 squared is 9 times 4 is 36 plus 1 is 37. So we've got 37 to the 3/2 minus, now if we plug 0 in, well, this is just 1 to the 3/2, which is 1. And so this still gives us a surface area, but we had to go to polar coordinates. Or we could have done this in rectangular, but it would probably have been an ugly trig sub. So chances are, if we've got an integral that involves trig sub, there's probably a smarter way to do it in polar coordinates. So that's going to be it for this section, because all we really wanted to cover was this main formula right here for arc length. We're going to look at another version of this in subsequent sections if we've got parametrized surfaces, but we'll do that later.